Okay, so hi everyone. Is it on? Yes. Okay. So I'm glad to introduce Angela. No. Okay. Angela Santos, who's visiting the IC this week until Friday. So Angela did her PhD at the University of Porto and in collaboration with the University of Birmingham. She obtained it in 2017. And the subject was the relation between magnetic activity and stellar oscillations. And in October 2017, she started a postdoctoral position at the Space Science Institute in Boulder. So she's working with me and other people in France as well. She's working mostly on magnetic activity, rotation, and the manifestation and impact of the magnetic activity on seismic properties of stars. But today she's going to talk about the work she's been doing with during her postdoc on measuring surface rotation of main sequence stars with Kepler.
Okay, it's on, I think. Hi everyone, thank you Savita for the introduction. So as Savita mentioned, today I'm going to talk about the rotation and photometric activity of Kepler stars that we have been measuring. And these are the people that I've been working with. So, but why it is important to know rotation and photometric activity levels for stars? One of the reasons is that we can use rotation and activity to estimate ages of stars. And these, and in particular for stars that we don't have astroseismology, this is one of the ways, or one of the only ways to get ages for stars. This is a plot, a famous plot from Schumann 1972, and we can see that with age, the chromospheric activity decreases, and also the rotation rate. So stars, as stars evolve, they slow down and also get less active. And we can use this these large samples of rotation periods and activity levels also to test and improve these relations that we use to estimate ages from rotation and activity. Another reason is that rotation and activity also affect the evolution of stars. And here, just to illustrate, so these are different stellar models with and without rotation and magnetic fields, and we can see how they change when including those properties in stellar models. So it's important also to constrain rotation and activity for such large samples to better understand the evolution, how they affect the evolution of stars. Another important point is that rotation and activity also affect the properties of the acoustic modes that we observe in the Sun and other solar type stars. And in particular, activity changes the mode frequencies. Here we have the frequency shifts in the Sun over time, so it's a temporal variation in the frequencies of the acoustic modes. And we can see in green, they changing over time, and in red we can see the sunspot number, so the frequencies vary in phase with the activity level for the Sun. And these changes are about 0.4 microhertz. And here it's one example for a Kepler star where we observe a larger frequency shift over time. And here we have the photometric activity index, which also indicates activity cycle going on. So the activity is increasing over time, and we see the frequencies also increasing over time. And here, these are the results from a paper led by Fernando. So if we don't know if the stars are active or not, and if they are in a high active level, we may bias our estimates for stellar parameters that we obtain from astroseismology, such as ages and radius of stars. So it's also important to know the activity level of these stars. Another property that changes over time is the amplitude of the modes. So the amplitude of the acoustic modes is observed to decrease over as the activity increases. So this is solar maximum, and we see the amplitudes decreasing towards the solar maximum, then increasing as the activity level decreases. And we also can see that for Kepler stars, here we have the height of the modes decreasing over time. And this means that activity suppresses the acoustic oscillations, and we do not expect to be able to observe oscillations for very active stars. So we are limited to less active stars for astroseismology. And this is shown by Savita. Here we have the photometric activity index and the rotation period, and in black we have the stars without oscillations being detected, and in red the stars with oscillations detected. And these dashed lines mark the solar minimum and solar maximum values. So we can see that for stars that are more active than the Sun in the maximum, we only detected oscillations for a few stars. And if you care more about exoplanets and stars, rotation and activity is also important for the exoplanet science. And basically, rotation and activity can mimic and hide the signal from exoplanets, and they also affect the habitability of the exoplanets. So it's also important to better characterize these stars. And we plan to measure rotation and photometric activity for all F, G, K, and M main sequence stars and subgiants observed by Kepler. And we have been focusing first on the K and M main sequence stars. So today I'm going to show only the results for M and K stars. And there are previous studies of rotation for Kepler stars, so why bother to reanalyze all the data again? So one of the reasons is that we use the full length of the Kepler observations, while other previous studies didn't use the full length. We also use different time series, calibrated in a different way than the others, and I will try to show you that it's important to have proper light curves for these studies. We also use the latest update of the KIC catalog, and we also try to identify possible polluters such as red giants that are misclassified or classical pulsators. And finally, the method that we use to recover rotation is also different from the previous studies. So, and how we measure rotation? So, if the star is active and it has star spots in its surface, as the spots follow the rotation of the star, the surface rotation, they produce a modulation of the light curve. When they are in the visible side, we get less flux compared with when they are in the invisible side of the star. And the period of this modulation is related with the surface rotation period. So basically you can use these spot-induced modulations in the light curve to infer rotation. And the good news, or one of the advantages of Kepler data is that Kepler observed the same field of view for 4 years. So we have a long time series that is also important to characterize magnetic activity and also rotation. And this is just 3 examples of Kepler light curves for 3 different stars with different periods. So we can see the spot modulation in the 3 of the light curves. This is a fast rotator, a slow rotator, and a star with an intermediate rotation period. And one of the methods that has been used to recover rotation for Kepler stars is the program analysis. Then the autocorrelation function of light curves was used to provide the largest catalog to this date of rotation periods for Kepler stars. And the method that we applied combines autocorrelation function of light curves with wavelet analysis of the light curves. And this method was shown in this paper in 2015 using artificial data. That this method was shown to be this method providing the most reliable set of rotation periods and also the most complete set of rotation periods. So this is, each panel corresponds to a different team with different methods, and you can see that comparison between the detected and true period is best for the method that we apply. The sample is composed by more than 26,000 stars, so K and M main sequence stars. And then we try to identify all the possible polluters. So I have a few examples here. We have a classical pulsator that is misclassified as a main sequence K star. And this is a red giant that is also misclassified. You can see here the P modes. This is the eclipsing binary, and we remove all the eclipsing binaries because the eclipses can be confused with rotation. And these are some of the targets that we also flag as possible classical pulsators or binary systems. And in particular, this one, this type of target, which resembles the RR Lyrae star. This kind of candidate can also be a close-in binary. There's some evidence that this can be binaries instead of classical pulsators. And we also have other binary candidates in our sample. So this marks the Gaia binary candidates and the tidally synchronized binary candidates in green, and in blue the Gaia binary candidates. We flag them in our sample, but we still analyze them. The light curves that we use are obtained with the KADACS. This is the meaning of the acronym, but summarizing, these light curves are optimized for seismic studies, and they are also proper for rotation and activity studies. The main difference with the normal light curves is that the apertures are customized, the software corrects for instrumental problems, and also properly stitches together the different quarters, Kepler quarters. The gaps that are smaller than 20 days are filled, so that is also important for some stars. And we also use 3 different filters. And this is the light curves for one star obtained with the 3 different filters, which for this star doesn't make much difference. But for this star, for example, we can see that they are different, the light curves obtained with the different filters. And the main reason why we use the 3 filters is to make sure that we are not getting the harmonic of the true rotation period instead of the rotation period. And you can see here in the first light curve obtained with a 20-day filter, the signal from the rotation is filtered, and if we run normally our rotation code, we would get the harmonic instead of the rotation period. So that's one of the reasons why it's important to use different sets of light curves obtained with different filters. And we also analyze PDC-MAP light curves, the ones that are commonly used. And the reason why we use also compare with these light curves is because the apertures are different from KADACS and PDC-MAP, and usually the KADACS apertures are larger, which means that sometimes we get photometric pollution by nearby stars. So we make sure that the signal is present in both sets of light curves. Then these are basically the representation of our method. So this is the wavelet from the light curve, and the darker colors mark the rotation period of the star, and this is just the sum of the power. So this is our first estimate for rotation. Then we have the autocorrelation function, and we have our second estimate for rotation, and the composite spectrum, that is the product between the two, highlighting the common periods, and this is our third estimate. So for the automatic selection, basically all these 3 estimates have to agree with each other, and they also have to agree between the different filters. And then we also imply a threshold in the height of these peaks. And this is for the automatic selection. And then for the stars that don't obey the criteria that we impose, we visually check them for this sample. And having the rotation period for these stars, we then compute the photometric activity index. That is measured over subseries of length 5 times the rotation period. And the final value that we give is the average of those values. And yeah, I forgot to say, SPH is the standard deviation of the light of the flex over those subseries. So it's a measure of the amplitude of the spot modulation. And the SPH was shown to be well correlated with other sunspot proxies for solar proxies for activity. Sunspot number, the flux at 10.7 centimeters, the chromospheric index, and the frequency shifts. And it was also shown to be well correlated with the chromospheric index for Kepler solar analogs. And this is the summary for our first study. For the K and M stars, we detect rotation for about 60% of the sample. And for stars that we don't detect rotation, we also flag them with different flags. And for some stars, we don't see any sign of rotation signal. And for other stars, we see rotation signal, but there's usually large instrumental effects that don't allow us to say exactly or to be sure on the rotation period for that star. And so here we have the rotation period as a function of effective temperature, and we can see that rotation period decreases slightly with effective temperature. And we also see that there's two sequences in rotation, a slower rotator sequence and a fast rotator sequence. And this was also found previously with other studies. This is for the SPH, the photometric activity index. And so we see that the range of values that the SPH takes, it's larger or it's wider as the effective temperature increases. And this is the SPH as a function of the rotation period, where we see that the fast rotators are more active than the slower rotators over here. And this is just the values for the sun at solar minimum and solar maximum. And we also can see the two sequences in rotation period here. And so I forgot to say, but in these plots we don't have any of the possible polluters, so we think, or there's no evidence for these stars not being single main sequence stars. And here I overplot the binary candidates. So in gray it's all the stars in the previous plot, and in the other colors we have the binary candidates. The Gaia binary candidates are all over the parameter space, while the tidally synchronized binaries are correspond to fast rotators with large values of SPH. And the targets that we flag as type 1 classical pulsator or close-in binary candidates also occupy the same parameter space as the tidally synchronized binaries. And the comparison with the previous largest sample of rotation periods, so McQuillan et al. 2014. For the stars that we have in common, the agreement is very good, and we can see that most of the stars fall close to the one-to-one line. But we detect more than 4,000 new rotation periods in comparison with that study. And that could be because of a combination of the light curves that we use, the length of the observations, and also the rotation method. And we also can see here that we also are able to detect rotation periods for fainter stars than in McQuillan. And in comparison with the PDC-MAP light curves, so I said previously that light curves, the set of light curves that we use is also important for these kind of studies, and we can see here that there's a difference for the rotation periods obtained with the PDC-MAP light curves and the KADACS light curves. So these two histograms correspond to the same exact stars, and we can see that this distribution of rotation periods for the PDC-MAP light curves is shifted towards shorter periods, and also with these light curves we cannot go to longer periods. And one of the reasons is that in PDC-MAP light curves, they apply a 20-day filter, and it's not applied in all quarters, but they often apply this to a 20-day filter, basically. It's filtering out the rotation signal, and we obtain the harmonic of the rotation period instead of the rotation. And this is the summary for this study, and we plan to extend this analysis for F and G stars, but we also plan to go further, so we already started doing some other extra studies for these stars, K and M stars. First, we want to detect or estimate active region lifetimes for these stars, and we estimate the lifetime of the active regions using the decay of the autocorrelation function. So we expect that the decay of the autocorrelation is related to the lifetime of the active regions. And these are some of the preliminary results. So we have lifetimes as a function of rotation period, and we can see this spread to the two sequences in rotation period, but we can see that lifetimes increase for faster rotators. And this is lifetimes as a function of the activity index. So for more active stars, the lifetimes are also longer than in comparison with less active stars. And this is the same results, but in the SPH rotation period diagram, and we see here the shortest lifetimes for slower and less active stars. Another property that we are planning to obtain for all these stars is an estimate for differential rotation. One of the methods that we will apply, we are tested in 2017, and these authors, Reynolds and Arlt, proposed a method to obtain the sign of differential rotation, and we have shown that the method was not completely valid. And here, just to illustrate some of simulations, and the red points correspond to the simulations for which we detect the opposite sign of differential rotation. So we went further and we tried to understand why we get false negatives or false positives, depending on which is the true the input rotation. And the property that this method is based on is the peak-height ratio. So this peak-height ratio is the ratio between the height of the harmonic in comparison with the height of the rotation period. And this peak-height ratio is a measure of how sinusoidal is the light curve that we are analyzing. So if the light curve is not very sinusoidal, there's extra power in the harmonic in comparison with more sinusoidal light curves. And here, just the same image as before, just to illustrate, for star spots that are also always visible, the light curve is more sinusoidal than for star spots that are only visible for a short time of the rotation period. We can see here the flat tops when the spot is not in the visible side of the star. And so this sinusoidal shape is dependent on the visibility time of the spots. And this is what we show here, the peak-height ratios, the measure of the sinusoidal, how sinusoidal is the light curve, as a function of the relative visibility time of the spots for different inclination angles and for different latitudes. And this visibility time is dependent on the latitudes of the spots and also the inclination angle. So we can see here that for a given inclination angle, there's a well-defined relation for the peak-height ratios. So if we know the inclination for the stars, we may be able to constrain latitudes of spots. And we also shown that these peak-height ratios are not strongly dependent on other properties that usually other methods such as spot modeling are dependent. And here is the first application that we, for real data that we made with this method. So this is a Kepler star, solar type star observed by Kepler. We know the inclination angle from asteroseismology, so we know how we expect the Picard ratios to behave. And we have the periods that we detect and the Picard ratios for those periods. So we can infer the latitudes of the spots. And this is what we did. So this is the absolute latitude as a function of periods. So we infer the latitude for each period that we detect. And we also use different, the full length of this light curve and subseries of the light curve. And we then fit rotational profile to the data, to the results. And for this star in particular, we obtained that the differential rotation is more than twice stronger than the Sun, the differential rotation in the Sun. And this is also in agreement with more recent analysis for this star that also show that the star should have a stronger differential rotation than the Sun. But there are some problems with this method. One of the problems is that if the periodogram is complex and there's several peaks in the periodogram, the heights of, or each peak influences the other, and the heights are affected, so the Picard ratios are affected. There's also lifetime and spot evolution, so it also produces peaks in the periodogram and changes the peaks related with the rotation period of the stars. And if there are spots in opposite sides of the star, we also detect so the Picard ratios are also affected because it introduces extra power in half of the rotation period. So we also plan to study the distribution of rotation periods using different shorter subseries of light curves, and that will give a lower limit for the amplitude of differential rotation that is also related with the alpha that we measure from the other method. Now, so the analysis that we have been doing and we plan to continue doing for the Kepler data is also valid for other missions like K2 and TESS and future Plato. And here just to illustrate a few light curves from TESS. And one of the problems with TESS is that light curves are too short, or most of the light curves will be too short for this kind of analysis. So for these stars in particular, it's okay. So these are fast rotators, and we can clearly see the spot modulation, but here we can see that there's some signal, but it's within the noise, and we are not sure if this is rotation or other kind of brightness variability. And this results in this comparison. So this is for the same stars, rotation periods obtained by different teams. We are team 1, and we can see for some stars there are huge discrepancies between the values that different teams obtain. And this is because one of the reasons is the light curves that are too short, and different methods will provide different answers. Here is the summary of our results of team 1. So this is the chromospheric index for activity that we didn't know before analyzing the data. Well, and this is the SPH that we measure from the light curves. And this is the activity-activity relation, the fit to the activity relation. So the black dots are the ones that were automatically selected based on the method, the criteria that I mentioned before. And then we have the green and red crosses, the green plus sign and red crosses that are stars that we remove or add after visually check these stars. And we can see that the visual check of these stars was important to include more stars around the activity line. But when we were looking at these light curves, we didn't know this property. We only were trying to decide whether we believe that the light curve was showing rotation or not. So that was for SPH, but for the rotation period. So Rossby number here, it's the ratio between the rotation period and the convective turnover timescale. And this in gray is expected relation based on Mount Wilson targets. And we can see that most of the stars follow below the line. And this is because probably for the sum of the stars we are measuring a lower limit of the rotation period. And again, this is related with the short light curves that we have from TESS. So I leave you the summary. I just want to mention that we are in the way of providing the rotation periods and SPH values for F and G stars and also subgiant stars observed by Kepler. And since we basically visually checked 40% of the sample, for the next sample of F and G stars, we are applying machine learning techniques to decrease the visual checks that we need to do. And yeah, basically this method is also valid for other missions besides Kepler. That's all. Thank you.
Thank you, Angela. Okay, so we have time for questions. Any questions?
Well, first of all, Angela, thanks a lot. It's very nice work, very extensive, and it requires time for think on many things you show us. One question about how low, how far can you go with your technique in terms of rotation periods? You've been using 1400 days of data from Kepler. Mm-hmm. So the longest period you can figure out, it's about few hundred days.
Yes.
How far can you go into the above red giants regions where rotation periods are even longer? You few samples of the rotation with your technique, I mean.
Yeah, so for this sample we are not looking at red giants, but we have been looking, and this previous student of Rafa Garcia was looking at red giants, and I believe that most of the red giants we are not able to see a rotation signal, maybe because the rotation is too long for the 4 years of data. And also with our method, usually we are able only to go to a few, less than 200 days. With the wavelet analysis, we only go to 100 days, but with the ACF we can go further. And those stars basically correspond to the ones that we have to visually check. But yeah, we cannot go very long, very long.
Okay, and just one technical thing. When you say composite spectrum, CS, is just a kind of collapse wavelet spectrum?
The collapse is the global wavelet spectrum.
But when you say CS?
It's the product between the global wavelet spectrum, so the collapse of the wavelet analysis, and the autocorrelation function. The normalized global wavelet power spectrum and the normalized autocorrelation function, and basically it highlights all the peaks that are common in both methods.
Okay. Thanks. We'll talk tomorrow.
More questions? So I have a silly question. I don't work on stars, but so what's the origin of the relation between effective temperature and the rotation period? What is it? Is this known? Is this age, or what causes that?
Yeah, I don't know the reason behind.
Mm-hmm.
Around 1.2, 1.3 solar masses, where so more massive stars are slow down less rapidly because they have a thinner convective zone, so they are less they have less magnetic braking compared to the lower massive stars. So that's already defining these two different ways of evolution of the rotation of the stars. So I think that's partly what we see with the effective temperature.
Thanks. Any comments or questions? Okay, let's thank Angela again for a nice talk. Thank you.